Okay, so in this video we are going to talk about momentum methods for a single particle. So we will be talking about both linear as well as angular momentum. So suppose that you have a particle, net force acting on it is given by F. So this is net force acting on the particle. It has some velocity v and mass m. So you know already that linear momentum, we denote it by capital L in this course. So linear momentum L is defined as mass of the particle into its velocity. Now you know from Newton's second law that net force acting on a single particle is equal to mass of that particles times its acceleration, and acceleration is nothing but time derivative of the velocity of the particle. Since mass of the particle is constant, we can take it inside mv over dt, and this is nothing but mv is linear momentum. So therefore what we get is force is equal to rate of change of linear momentum, which is another way of expressing the Newton's second law. Now this dl over dt is equal to net force F can be solved as a differential equation like this if we integrate it. So if I write dl is equal to F dt and integrate both sides, so I integrate force from time t1 to time t2, and the change in momentum is between force t1, its momentum is L1, and after at time t2 its momentum is say L2. So then I'll get from here L2 minus L1 is equal to integral of F between the interval t1 and t2. This quantity, the integral of force, net force within an interval, is called impulse or linear impulse. So this is linear impulse I, which is a vector quantity. So from this equation we can write L2, momentum of the particle at a later time step, is equal to initial momentum plus impulse between the interval. We can also express impulse I like this. So I is equal to F dt from t1 to t2. So if I multiply and divide this by 1 by over t2 minus t1, so I am dividing this expression by t2 minus t1, and I also multiply it by the same quantity. Now notice that this thing is from definition of average, is the average force acting between this interval t1 to t2, and this is the length of the time interval, say it is delta t. So from here we can write impulse is equal to average force acting over an interval and the length of that interval. Therefore linear momentum at a later time instant can be related to linear momentum at an initial time instant plus average force acting over that time interval times the time interval itself. Now if net force acting on the particle F is 0 between T1 and T2, so there is no net force acting on the particle between this interval T1 and T2, then impulse I will be 0. Then from this equation we can write L2 is equal to L1, which is basically conservation of linear momentum. So this is conservation of linear momentum. It can also be written in this form, that since you know that F is equal to L dot and F is going to be 0, so then conservation of linear momentum can also be written in this form, that is the time derivative of momentum is 0 when net force F acting on the particle is 0. So this was for linear momentum. Now we will move on to angular momentum. So let me mark here. So this was linear momentum. Now we will move on to angular momentum. So suppose that this is your particle, it has velocity v and mass m and net force F acting on the particle, and here is my coordinate system. So here is my origin, and now suppose I take some point A, which is my reference point. It can be fixed or moving, we will see. So right now we are not telling that it is fixed, so it is just any point A. So the vector, the position of this point A, let us denote that by RA. So let me first draw all the vectors. So this is the position of reference point RA, this is the position of the particle, and this is the position of the particle with respect to A. So this is R minus RA, relative position of the particle with respect to A. Now angular momentum, we will denote this by H. So angular momentum of the particle has to be defined with respect to some point. So for example, angular momentum with respect to point A is defined as position of the particle with respect to that reference point, so which is R minus RA, cross product with the linear momentum of the particle. So basically this comes out to be r minus ra cross mv. So this is the definition of angular momentum. So this was definition of linear momentum, and this is the definition of angular momentum. Okay, let me rub this. Now, so we have already seen that time derivative of linear momentum is equal to force acting on the particle. What about time derivative of angular momentum? So if I take time derivative of angular momentum, so what will come out? I have to differentiate this expression. So first I will differentiate r minus ra while keeping mv fixed, plus then I'll keep r minus ra fixed and take time derivative of mv. Now this is basically velocity of the particle. This is velocity of the point A, and this is acceleration of the particle. So we get time derivative of angular momentum of a particle is equal to v minus va cross mv plus r minus ra cross ma. Now from Newton's second law, F is equal to ma. So we will put F here, and we will expand this bracket, we will open this bracket and distribute this cross product over V and VA. So what we will get is HA dot is equal to V cross MV, which is basically 0 because V cross V is 0 by the property of cross product, minus VA cross MV plus R minus RA cross, I will replace MA by net force acting on the particle. So therefore I will get HA dot is equal to minus VA cross MV plus, what is this quantity now? R minus RA is the vector joining the particle, joining A to the particle, and cross product with F. So this is basically moment of F with respect to point A. So I'll write this as MA. So this is moment of net force with respect to point A. So this is a general relation for any point A. But now if we want to simplify that relation, we would like to make this term 0. So this term can be 0 for two cases. So V cross MV is 0 either when VA is 0. This implies fixed point A, when the point A is fixed, and when VA is parallel to V, so they have same direction. So when VA and V have same direction, so for these two cases, we will get time derivative of angular momentum is equal to ma, or I can write alternatively ma first. So moment of the forces acting on the particle taken with respect to A is equal to h a moment of momentum, that is angular momentum of the particle, and its time rate of change. Okay, so this relation is very similar to the relation for linear momentum that we saw just a while ago. But remember that this is valid for A fixed or VA, velocity of that point is in the direction of is along V. Only then this relation is valid. So the case that we usually see in problems is this case, that we take A as a fixed point and use this relation. The second case is rarely used. All right, so now since we have got this relation, we can integrate this. So we can write dHA over dt is equal to ma. Now if I write dHA is equal to ma dt and integrate both sides, so this side from T1 to T2, this side from angular momentum HA1 to angular momentum HA2, so I will get is h angular momentum with respect to A at later time instant minus angular momentum at the initial time step is equal to angular impulse, that is m a dt T1 to T2. So I'll write this here, HA2 is equal to HA1 plus integral, so I am not giving you any special sign, or you can use J, for this, is equal to J plus J. Now if we want to use conservation of angular momentum, we have to make this J as 0, right? So if somehow this J is 0, for that case HA2 will be equal to HA1, and that will be conservation of angular momentum. So when will be J 0? So JA equal to m a dt or we can also write this as h dot a dot is equal to m. So if I am A, Now we want HA dot to be equal to 0, which also means, which is equivalent to HA2 is equal to HA1. So this equation is valid when m is 0. Let me write this in red itself because this is important. So this is valid when moment with respect to A is 0. When will be moment 0? So moment with respect to A is defined as R minus RA cross F. So this thing is equal to 0 in two cases. Either when F is 0, so no net external force, so no net external force. So this cross product is 0 either because there is no net force acting on the particle. So in that case linear momentum is conserved and angular momentum is also conserved, taken with respect to a fixed point A. The second case is when the force which is acting is along R minus RA. When this happens with proper choice of coordinate system and in certain cases. For example, in case of gravity. Let me show you how. Suppose this is my coordinate system. So let me stick with 2D only. This is the origin. So there is some mass here, say for example there is a large mass here, there is a small mass m here, and this is the force of gravity acting on them. So the force, I will not write the expression for force, I will just write F. The force is, so if I put this as theta and choose a cylindrical coordinate system, ER E theta, so the force is in the negative ER direction. So F ER, whatever its value F is, you know from Newton's law of gravitation what F is, but that is not the point here. The point is that the direction of F is negative of ER. Now if you choose your A point to be this is your reference point about which you are calculating momentum. Okay, so what we get is, yes, so we have this moment about O, which is a fixed point. So instead of A now I have O, and I have this O is origin and this is my position vector R minus RA is now 0 because this A is taken at origin. So taking A as O, so we can do with any fixed point A, so we have taken O in this example. So this will be 0 vector, so you don't need to write this. So this will be R cross minus F ER, and you know that R is nothing but R ER in cylindrical coordinates. So this ER and ER cross, so this ER cross ER, this will come out to be 0, right? So if that is the case, then what will happen? HO dot will be 0. Now if I write my expression for HO and then differentiate it, what I will get, let us see. So HO is R minus RA, so RA is 0, so this will be just R cross linear momentum of the particle, which is m times v. And you know that in cylindrical coordinates v is VR ER plus v theta e theta in polar coordinates. So I'll write this expression. So I'll replace R by ER, cross product with VR ER plus v theta e theta. Now HA dot is 0 in this case. So this kind of problem is called central force motion, when the force is always directed towards the center, just like in the example of gravity. So this is central force motion, and angular momentum is conserved for central force motion. So linear momentum for the particle is not conserved here, but angular momentum is conserved. Why? Because moment is 0. Why? Because force is along your force arm. Anyway, coming back, so HO dot we will find. Before that we have to find this HO. So when you will take cross product, ER cross ER will become 0, and ER cross E theta will be EZ. So this comes out to be R V theta EZ, and you know V theta is nothing but R theta dot. So in from polar coordinates we know that the expression for VR and V theta are R dot, and this is R theta dot E theta. So V theta is R theta dot. So I'll write here R theta dot, so R square theta dot EZ. So now I'll differentiate this expression for HO. So R square EZ over dt, and that will be twice R dot theta dot plus R square theta double dot EZ equal to 0. So this is equal to 0. Also, this is one form of conservation. Another form is that HO is a constant. So using that HO is constant, we will use the expression for HO. This implies R square theta dot EZ is equal to constant. Now EZ itself is a constant, it does not change its magnitude or direction, it always points along the k direction, perpendicular direction. So therefore we can write R square theta dot is a constant, and this is basically expression of Kepler's second law, if you integrate this r square theta dot, what you will get is, you will get the area sweep between theta 1 and theta 2, and that area will be constant, you know, from Kepler's second law, if you have studied. If you have not, then don't worry about that. Anyway, so for central force motion, r square theta dot is a constant for central force motion. What is central force motion? It is that motion in which force is always directed towards the origin, towards the point about which you are taking your moment. So that's it for momentum of a particle.